Excellent. Yes, I got a little Zoom pop-up saying that my microphone wasn't working, so I disconnected it and reconnected it, and now it seems to work. We're at 10:46. Let's give it another 2 minutes or so. Give people a chance to get reconnected. Oh, and Andre, I should tell you, I have to, well, I guess we exchanged that email this morning. So
yeah, no, that's fine.
I have
That's not a big deal.
check out a little early today. So.
You know, I had to do that last week several times.
Okay.
That's one of the downsides of not being there, is that you can
still
do
have
lots
to,
of things at the same time.
Right, exactly. which you actually can't, but you don't realize it as much when you're.
Yep, it's harder to say no.
Yeah. Okay, so the number of people is creeping up there. I think maybe we should get started and thereby encourage people to join more promptly. Okay, so welcome back, everybody. Today, right now, we have Andre de Gouvea's second lecture on neutrino mass models, and please take it away.
Okay, so I hope everybody can see my screen as well as they could yesterday. And again, let me just quickly recap what we spent the last hour and 15 minutes doing, which was taking fermions and expressing them in terms of two-component biofermions. And I spent a lot of time trying to connect that with what I hope you know about Dirac fermions. And for example, you know, we got to write down Lagrangians that look like this. And that I claim is the same as the Lagrangian for a Dirac fermion with mass m. And then I talked about these objects here. This is a left-handed biofermion. This is a right-handed biofermion. And one thing which I forgot to say, but it's going to be very important since we'll start talking about the Standard Model, is about other symmetries that this Lagrangian has. And again, it's a super simple Lagrangian. And I want to mention that now because we will talk about this a lot. This also came up in the questions, which has to do with other symmetries that you can speak of. And the most important thing to appreciate is the fact that these kinetic energy terms, and again, I'm going to highlight them like this is a kinetic energy term, this is another kinetic energy term. They allow for a U1 symmetry, or they allow you to multiply, for example, your chi field, which I'm writing down here, by a phase, and the kinetic energy term of the Lagrangian is the same. And I can also multiply this xi field, which is the right-handed biofermion, by a different phase. And you notice that the kinetic energy terms of the Lagrangian are invariant under that. The mass terms, on the other hand, are not, because the mass term is this mixture of the chi and the xi. And you notice that if you choose to rotate chi by a phase, and you rotate xi by a different phase, the Lagrangian is not invariant under that. It is invariant, however, under the hypothesis where the two thetas are the same. So if the two thetas are the same, then the mass term is okay. Okay? And again, this is something that you hear about. Generically, if you write down what are the transformation properties of the Dirac field, if you rotate the entire Dirac field by a phase, that's equivalent to rotating the left-handed chiral component and the right-handed chiral component by the same phase. And you also learn about these chiral rotations, which is a rotation that has a gamma 5 in it. And that's the rotation where you rotate chi left by one phase and psi right by the opposite phase. Okay, so that's an important thing to appreciate. And of course, generically, and this is what we're going to see in the case of the Standard Model, this also is true for gauge symmetries. And again, this is the other thing which is very important. Remember, the gauge symmetries are these things in blue here. They live, as far as the fermions are concerned, the gauge interactions live in the kinetic energy part of the theory. And if you look at it, the really important thing is that the gauge interactions always show up in either in a psi-psi form or in a chi-chi form, which means that in principle, you are allowed to give right-handed chirofermions one gauge charge and left-handed chirofermions a completely different gauge charge, and nothing bad happens. The only bad thing that potentially happens, which is what happens in the Standard Model, is that the mass terms are something that you have to worry about. And this is what we're going to talk about. Then, just as another reminder, the other thing that we did is we did away with the right-handed fields by replacing them with their complex conjugates, if you want to think about it that way. And the story is exactly the same. Again, very, very generically, if I only stare at these kinetic energy terms, the chi and the chi-c can be rotated by a phase by themselves, and the kinetic energy terms are invariant. So this doesn't care if you rotate this guy by a phase and this guy by a different phase. But on the other hand, if I have a mass term, which is this mass term that we've been talking about a lot, then if you want the mass term to be there, then you notice that the chi-c and the chi have to rotate by equal and opposite phases. Okay, and it's the mass term. So if you want to think about this, it's the mass term that tells you, so if the mass is here, and if the mass term looks like this, it's the mass term that's telling you that this chi and the chi-c particles are related to one another, and in some sense they are. In some sense, one is related to the complex conjugate of the other one. So the mass term is the thing that tells you that chi and chi-c have some relation to one another, which is why we picked this name to begin with. That's why we called it chi and chi-c, because that was a reminder for us that because this mass term is here, this chi and chi-c are secretly part of the same Dirac fermion. If the mass term were not there, then the chi and the chi-c would be completely different objects. Okay, so we're going to go back to the Standard Model. And I'm happy to, when I saw that Lisa also talked about this, mostly in the context of there being lots and lots of families. I want to go back and remind you of the last thing that we wrote down, and we're not going to care about families very much because she's going to do all of that hard work. But I do want to go back to the Yukawa sector of the Standard Model, which she did talk about, hopefully because that will help me introduce some language. So again, these are the fermion fields in the Standard Model. It's this acutely, if you want to remember yourself that way. I wrote it using only these left-handed biofermions, which is why we have these fields with C's in it. And if you are confused by this, the way that you want to think about this is the following. If I look, say, at the Q field, it has a U in it. And what this field here does is that it destroys left-handed up quarks. The UC, on the other hand, what it does is it destroys left-handed anti-quarks or anti-up quarks. And the DC here destroys left-handed anti-down quarks. And the handedness here, unfortunately, refers to chirality. It has some relationship with helicity, but that's a more complicated story that we won't talk about. I will bring this up a little bit later in the context of neutrinos. Okay, so again, these are all of the quantum numbers that we have. So the Q's are triplets, the UC and the DC are anti-triplets, the L doesn't have any color, the EC also doesn't have any color. From the SU2 perspective, the L is a doublet. It contains the neutrino and the charged lepton. The Q is also a doublet. It has the up and the down quark. Everybody else are singlets. And then, of course, there are these hypercharge assignments. And the hypercharge assignment is chosen, if you remember, if you want to remember this in lots of different ways, it's chosen in a way that you get the charges right at the end of the day. Okay, so this is the Standard Model. And if we stare at it, our next job is to write down the Lagrangian. And since we're interested in masses, our job here is to form as many fermion bilinears as we can. So the idea is, remember, I mentioned the fact that a mass term is a fermion bilinear. It's a combination of two fermions in a way that's Lorentz invariant. And then there are two kinds of mass terms. One are Majorana mass terms, which is a bilinear of one field with itself. And the other one is a Dirac mass term, which is a bilinear of one fermion with a different fermion. What's really interesting about the Standard Model is that if you stare at this table, there is no bilinear fermions that you can write down that's also gauge invariant. And this is a thing that's very, 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 very important. And again, that's the thing that everybody knows, but I want to emphasize that because it's so important. So for example, you know, if you try to make a bilinear out of these two fields here, the colors don't work out. If you try to make a bilinear out of these two fields here, the SU2 charges don't work out. If you try to make a bilinear out of these two guys here, the SU2 charges don't work out. And you can look at all of the different combinations, and basically a generic prediction of the Standard Model is that fermion masses are 0. And as everybody knows, this is not a very good prediction because it turns out to be incorrect. And the way that we fix that is by adding a new field. And of course, we have to add this new field for other reasons as well. And that's the Higgs field. And the Higgs field for us, I think, will be the same that Lisa talked about. It's this one. It has a friend, which is the complex conjugate, but not, it's the complex conjugate and then flipped version of the field. And you don't really have to use that to write everything down, but it's convenient to do it this way. And I'm running out of space. So it looks like this. And then the key thing is that it has hypercharge plus a half, and this guy has hypercharge minus a half. Okay, so that's the idea. So again, coming back to what the story is that I can't write down any fermion mass in the Standard Model, period, because that is inconsistent with gauge symmetry. So the fermions are not, they don't allow me to write down any mass term at all. Now, because the Higgs boson exists, I can do the next best thing, which is I can write down Yukawa couplings. And of course, that's the way this works. So for example, you notice that if I take a Q with a UC or a Q with a DC, that's a fermion bilinear. So this is actually Lorentz invariant, but of course it's not invariant under SU2 cross U1. This, by the way, is also a color singlet, so this works out fine. On the other hand, if I add a Higgs here, and if I add a Higgs twiddle here, then you can quickly convince yourself that this is gauge invariant, because Q is a doublet. I can combine that with the Higgs, which is another doublet. So the doubletness works out. The same goes for Q and the H twiddle. The H twiddle is also a doublet. So this also works out. And then we can check that the hypercharges work out. This is a sixth. This is minus 2/3. This is plus a half. This adds up to 0. This is a sixth. This is plus a third. This is minus a half. And I hope this also adds up to 0. So these are all terms which are allowed in my Lagrangian. So I can write those down. And then there's another term that I can write down, which is, which is one for the charged leptons, which is this LEC Higgs twiddle. And again, this says hypercharge minus a half. This is plus 1. This is minus a half. So the hypercharges add up to 0. So there's a question here. So from my notation so far, H and this H twiddle are different objects. No, they're not. They are just one object and the complex conjugate of that object multiplied by I sigma 2 in a weak isospin space. So basically the challenge here is the following. So the question that you want to ask yourself is, so I have a bunch of doublets amongst my fermions, you know, the Q the Q is a SU2 doublet, the L is an SU2 doublet, and then I have the Higgs, which is also an SU2 doublet. So the question you need to ask yourself is, okay, so given these two doublets, what are the ways of forming a weak isospin singlet? And it turns out that there are two ways of doing that. One that uses the Higgs field, the other one that uses the conjugate of the Higgs field. And this is something which is a fun feature of the SU2 group, and I'm not going to talk about that. But hopefully, this is relatively a simple notation, so everybody uses that. Okay, so let me continue. So of course, this is if I add the Hermitian conjugate to this, this is going to live inside of my Lagrangian up to some silly minus sign. And then, of course, we know that this will lead to masses because the Higgs has a vacuum expectation value, which is this thing here. And again, you know, the Higgs twiddle, which again is related to the Higgs. So I will answer this question in just a second. The Higgs twiddle has a VEV that looks like this. By the way, I made a mistake here, which is one of these guys here has a minus sign. Let's pretend it's this one. It doesn't matter, but that's just something to keep in mind. Okay, so one question is, in my Lagrangian here, should the Q's and the L's have a transpose? So let me answer that in two different ways. One is I'm pretending that there's only one family, so I'm not worrying about family space. If you were worrying about the family space, yes, the VEVs are switched. So sorry, the VEVs are switched. So I can fix that. That means I really have to remember to look at my notes because otherwise I'll make an infinite number of mistakes. So I was talking about whether there's a transpose here or not. And the way that I talk, so first of all, this is one family. If we were doing more families, there would be, you know, I's and J's here, you know, an I here and a J here, and blah, blah, blah. So I'm not talking about that because Lisa's talking about that. And now going back to the transpose, in the way that I define my notation, there are no transposes here because everything is in the dots that I didn't write down. So remember this, let me do a different color here. This Q is a, well, I'm not going to write anything, I'll just point. This Q here is a two-component fermion, and it's multiplied by another two-component fermion, and the implication is that they are dotted in the way that makes a gauge singlet. So that means it looks like the top component times the bottom component and flipped with a minus sign. So they form a singlet. Now there's another SU2 here just to make life more exciting, which is the fact that Q is an SU2 doublet of weak isospin, and H is also a doublet of weak isospin. And those guys are also dotted in a way that forms a singlet. So again, this is something which I will write. So for example, when I write QH, what this means is, remember, the Q looks like up, down. The H looks like H plus H0. So what this looks like is UH0 minus DH plus. That's what this means. Just like when I write QUC, this is a Lorentz invariant. So in that way, I don't have to worry about transposes and stuff like that. Okay, so that's all in the notation. And you can say, why would anybody come up with a new notation? The reason is I don't know. People come up with lots of different notations. But I do want to talk about this because it does make life a little bit easier for talking about neutrino masses, which is where we're going. And I do want to remind you that it is a widely used notation. So one of my hopes is that if you pick up a paper that writes down a Lagrangian, first of all, half of the authors don't really tell you what they're doing. They just write down the Lagrangian, and you have to decipher which notation they're using. And this notation is pretty widespread. And in some contexts, it is incredibly useful. So the hope is that when you stare at a Lagrangian that looks like this, that doesn't have any transposes in it, that only has a left-handed biofermions in it, you can understand how everything is properly contracted. Absolutely, yeah. So the question is, so all of the constructions are happening with I sigma 2, and the answer is absolutely. Because again, the I sigma 2 is the thing that allows you to combine 2 spin-a-halves into a spin 0, right? So that's exactly what I wrote here. So if you want, it's the contraction that goes like this. Okay, all right. So the reason I'm writing all of this is that this is how masses work. It's actually quite messy, but I do want to say how inevitable it is. And again, the key point is, because these are the fermions of the Standard Model, and because they have these charges here, I just can't write down any masses for anybody. The only way that I can do that is with the help of the Higgs boson via these Yukawa interactions, which is what I wrote down here. Now, the one thing that I will say lots of times is that the fact that it's easy to prediction. Neutrino masses are 0. This is a very hardcore prediction of this model. And it's almost correct, because neutrino masses are very, very small. They're not exactly 0, but they're just super tiny. Now, what does this mean? It means we need more degrees of freedom. So there's a question here in the chat. So I guess the idea is to form a gauge singlet by doing some gauge group theory. Is this notation easy to generalize for other gauge group structures? I think the answer is yes. As I think I mentioned, again, if you have other groups, you have to, and again, it's not just the group, but it's the representation. As far as particle physics is concerned, if you are a hardcore phenomenologist or if you just want to build models, what you really want to know about groups is how to form singlets. So if I tell you this is an object that transforms under some representation of some group, and here's another object that transforms under a different representation of the same group, how do I combine these objects to form singlets? And that's kind of what we spend a lot of time learning when you learn about, say, guts. If you're studying SO10 guts, E6 guts, or God forbid, E8 guts, your job is to learn how to write down singlets. What this notation is doing is it's telling you how to write down the Lorentz structure of the singlets by combining fermions into bilinears in this very specific way, because we're choosing to write down all of our fermions as left-handed biofermions. For the SU2 part, or the SU3 part, so for example, I didn't talk about the SU3 part, but clearly UC is a 3 bar, Q is a 3, so I'm combining a 3 and a 3 bar to form a singlet. And so that's the other feature of this that we have to contend with. And notice that there are no bars. Again, for people that like supersymmetric theories, they should be reminded of the fact that when you write down a superpotential using chiral superfields, there are no bars either. So this is a language that serves very well for writing down supersymmetric theories. Okay, so again, going back to the neutrinos, the challenge here is that the neutrino masses are predicted to be 0. So there's another comment. It's SU2, so an antisymmetric combo of 2 fundamental representation gives a singlet. For SU3, you need a 3 and a 3 bar, so that's correct. And that's what we have here. So I hope that's what you mean. And then of course, yeah, so again, it always depends on, every time there's a model, the key thing is somebody has to tell you, or you have to be the model builder that comes up with all of these numbers here. Of course, the way it works in the real world is we do experiments, and by doing experiments, we figure out what all of these numbers here are. And then once you know all of these numbers and you know the rules of group theory, you can start writing down these objects. Okay. So again, going back to the story, the only thing I want to say is that there's a prediction, neutrino masses are 0. That turns out to be wrong. So we have to do something. And that's what we want to talk about next. But before I do that, I want to remind you of what do we know about fermion masses? And again, I won't talk too much about this because Lisa is probably going to spend a lot of time, this is experimental. So we know a lot about fermion masses, and we've actually measured lots of them. Quark masses are kind of messy, but nonetheless, we know them more or less. We know the charged lepton masses very well. So it's kind of a fun exercise to write down what the fermion masses are and just to do it in a plot. So let's make a plot, which will be a challenge. So here is a mass line. Let's say this is a TeV. And let's say this is a log plot. So this is a GeV. This will be an MEV. This is a KV. This is an electron volt. And this is a milli-electron volt. Okay. So now let's start talking about masses. And I could have made this bigger. Let's see if we're going to get into trouble or not. So for example, let's talk about the uptight quarks. So the top quark has a mass which is around here. Right, it's 175 GeV. Then the next uptight quark is a charm quark. The mass of the charm quark is like 1.4, 1.5 GeV, and you can ask Tom about it later. He can tell you all about it. So the charm quark mass, somewhere around here. And then there's the up quark mass. We also don't know that very well. Let's pretend it's like 5 MeV. So this is an MeV. So 5 MeV is like here. Okay. So now let's talk about the down type quarks. So the bottom quark mass, again, it's a complicated question. Let's pretend it's like 4 GeV. So 4 GeV is kind of like here. That's for the bottom. Then the strange quark mass is also a kind of a messy thing. I think it's about like 90 MeV. So this is 10, so 90 is about here. And then we have the down quark mass. That's about 10. So let's put it here. Okay. So this is one of the interesting features of the standard model, is the fact that all of these different quarks have very, very different masses. And if you stare at this the way I wrote it, you notice that it spans about 5-ish orders of magnitude, 4 or 5 orders of magnitude, from here to here. And this is one of the things we don't understand, is why are these masses so very different? Now let's talk about charged leptons. So the largest charged lepton is the tau. The mass is a 1.777 GeV. Leptons are nice because we can measure the masses very well and we know what they mean mostly. So the tau is kind of like here. Then there's the muon. The mass is 105 point something MeV. So we'll put it here. Here's the muon. And then there's the electron, and the mass is around 511 keV. So this is 100 keV. So it's around here. I think I'm doing this right. So the electron mass is over here. Okay, and again, it is pretty weird how different these masses are. So you know, and this is something that Lisa will talk about, is we spend a lot of time writing down models to explain why these masses are so hierarchical. Okay, now we have to talk about neutrino masses. And let me do them in, I'll do yellow, they'll probably fail. So neutrino masses, as we know, there's a bound on the sum of the neutrino masses. And let's pretend it's, I don't know, 0.3 electron volts. That means that every mass is less than about a 0.1 electron volt. So let's put a bound here. This is a 0.1 electron volts. And we know that all of the neutrino masses have to be approximately less than that. There are a couple of other things that we do know. We know that if you have normal, if the neutrino masses are ordered in a normal ordering way, then the lightest neutrino mass can be 0. But the second lightest neutrino mass, or the one that, or the lightest one that we know is not 0, has to be bigger than about 0.01 electron volts. So 0.01 electron volts is like here. So this is a 0.01 electron volts. So we know that there's a neutrino mass that for sure lives here. And this, of course, is an upper bound. And then the other mass that we know about is the mass of the heaviest neutrino for sure has to be bigger than 0.05 electron volts, which of course 0.05 is hard to draw. So this was like, let's say it's somewhere here. That's not totally true, but let's pretend it's true. This is 0.05. So we know that there's a neutrino mass here. So we know that even in the limit where the lightest neutrino mass is super small, the two non-zero neutrino masses for sure live inside of here. So this is where the neutrinos live. And the reason I'm spending all this time doing this is, first of all, I want to remind you what it is we know about neutrino masses. But the other thing which I think is very important is to, first of all, at least in this optics, we do have pretty good information on the neutrino masses. So we've made a lot of progress in the last 20 years or so. But the one thing which I always like to emphasize is how weird the neutrino masses are. And I think the key thing is that neutrino masses are not 0, but they are very, very, very small. And I always like to remind people that if you look here, this is 5 orders of magnitude. And for people who like flavor physics, we spent decades explaining or trying to figure out why are there these 5 orders of magnitude amongst these different masses here. If you include the neutrinos in the story, this here is 6 orders of magnitude. And one thing that's very, that jumps out at people is if you look at the mass space between the electron and the top quark, you have all these other particles in the middle here, which is kind of nice. You know, that means if you're doing experiments and you're raising your center of mass energy, every once in a while you get to discover a new particle. So life was very exciting in the 50s and the 60s and the 70s and the 80s. In the 90s, because it took us a while to get to the top quark. On the other hand, in this area, let's do it this way. Here, there are no fermions. Or if you want, there's a gap, which is also kind of weird. And again, there's no physics here. This is all just being confused. But I think it's important to appreciate how different the neutrino masses are. And this is kind of a big deal. I think the message that people really believe in is that neutrinos are different. And the reason they're different is because their masses look weird. You know, they don't seem to match the pattern that people are thinking about. Now, this is not a scientific statement. It's kind of a gut check that you know, or numerology, if you want to think about it that way. So I think we always have to remind ourselves that that doesn't have to be true, but it certainly looks like it's true. Okay, so this is hopefully something that people can take home, is the fact that neutrino masses are not zero, but they're very different from the other masses. Just as a fun aside, you can ask, what about all the other masses in the Standard Model? You know, there's the W mass, the Z mass, and the Higgs boson mass. They all live here. So this is the MW, or sorry, MW, MZ, and M Higgs, which in itself is also a peculiar statement. Okay, so that's all I want to say about you know, stuff that everybody should already know. So now let's move to neutrino masses. And again, the key message before I start talking about specific details is the fact that we need new degrees of freedom. And the reason, again, goes back to this picture here, which is, I just told you that if you, even including the Higgs boson, if you try to write down a neutrino mass, you will not succeed. It's not possible, at least not at the renormalizable level. And I'll talk about that in just a minute. But again, you know, the really important message is staring at this fermion content over here and these gauge interactions, even with the help of the Higgs, you can't give neutrinos a mass. You need new degrees of freedom. I think it's in that sense, and Alex talked about this a little bit, it's in that sense that we're very confident when we say that neutrinos are physics beyond the Standard Model. And they're physics beyond the Standard Model in a very simple way. It just means that if you look at the Standard Model, it has a bunch of degrees of freedom in it, and they are not sufficient to give the neutrinos a new mass. We need to come up with some new degree of freedom. Now, the problem is there are lots of choices. And what makes it exciting is that the choices are qualitatively different. So that's what I'm going to be talking about for the next half lecture plus another lecture. That's kind of the key point is if you want to give the neutrinos a mass, you need to add degrees of freedom to the Standard Model. And there are lots of different ways of doing it. There's a lot of different kinds of degrees of freedom you can add. The degrees of freedom can be very light, they can be very heavy, they can be somewhere in between, they can be neutral, they can be charged, they can have new quantum numbers under new interactions. So the number of choices is gigantic. And of course, if you're in the business of phenomenology, the million-dollar question is, how do we tell the right answer? Again, just because we can construct 30 different models that explain why neutrino masses are not zero, chances are that nature picks at most one of those models. Nature will probably not pick all of them. So our job as phenomenologists or as particle physicists in general is to not just construct a bunch of models, but always keeping in mind that we want to find out what the right answer is. So that's what we're here for, and that's what I'm going to be talking about. And of course, we don't know the answer yet. We need more information, and I will touch on that as well. Okay, so that's the zeroth order introduction to this. The other thing I want to talk about is that there are two big choices. And again, remember, in our language, we have this field, nu, and this is a two-component biofermion. And we want this nu to have a mass somehow. That means that at the end of the day, I have to do something to my model. And at the end of the day, this nu has to have a mass. And remember, we talked about this. And the key point is that there are two different kinds of masses that I can write down. One is you can write down a Majorana mass. And that's a bilinear that looks like this. Or you can write down a Dirac mass, which is a nu married to somebody else, or partnered with a different field, which is not a nu. And of course, that will be the equivalent of a right-handed neutrino, which I'll talk about next. And I do want to emphasize that this is special for neutrinos. And the reason is, if we look at the standard model fermion content in the broken phase, we have some SU3 cross U1 electromagnetic interaction. And that's an exact symmetry of the broken Lagrangian. That's what's left over after the Higgs mechanism. And the key point is all of the fermions except for the neutrinos. So the up, the down, the electron, they all have charge. Electric charge. Which means that, if you wanted to write down a Majorana mass term for the electron, it would look something like this, or maybe it looks something like that. Or for the up quark, it could look something like this, or something like that. And for the down quark, these are all of the Majorana mass terms I could consider writing down for all of the charged fermions. And they are all disallowed by U1 electromagnetism. So this object here has charge -2, it's not allowed. Charge +2, it's not allowed. Charge 4/3, -4/3, -2/3, +2/3, and none of these are allowed. Okay, so just even in the broken phase, the electron, the up quark, and the down quark cannot have Majorana masses, period, because that violates conservation of charge. So there's a question. So since the neutrino lives in an SU2 doublet prior to electroweak symmetry breaking, do we think of the neutrino as becoming a Majorana particle after electroweak symmetry breaking? That's absolutely correct. That's the other thing, which I guess I can highlight here, is that in all of this, the neutrino still lives in a doublet. That means that whichever way you're going to give the neutrino a non-zero mass, it'll have something to do with electroweak symmetry breaking. So that's unavoidable because the neutrino does live in the doublet. And because, as we've already said, you can't write down the neutrino mass in the standard model before electroweak symmetry breaking. Regardless of how the neutrino gets a mass, that way of getting a mass will necessarily talk to electroweak symmetry breaking. It is just, in that sense, the neutrino is not different from the other fermions. They must get a mass through electroweak symmetry breaking as well. Okay? All right. So, if there are no more questions on these more philosophical things, yeah. The reason we don't have mu C in the table before is because it's neutral. Yes, and that's what I'll talk about now. So great, that's a good question. So 3A, this is going to be Dirac neutrinos. And again, let's go back to our table because it's a very useful table. If you stare at this table, the reason the neutrino does not get a mass is because it's missing a partner. So if you look here, and there's lots of fun ways of doing that. One way of thinking about this is, this is not totally correct, but it's kind of correct. If you count how many fermions there are, and you include, say, the colors and all of that, there's actually 15 fermions. So, so the Q has 6 degrees of freedom. So here's 6 plus 3 plus 3 plus 2 plus 1. This adds up to 15. And remember, masses are pairs of fermions that combine into a Dirac fermion. And if you stare at this, 15 is an odd number. That means somebody has to be left out. So everybody pairs up to get a mass, but because the number of fields is odd, somebody's left out, and that's the neutrino. So that's the story. And of course, how do we do better, or how do we fix that, is we can add a partner for the neutrino. And that's this mu C field. So I was going to do that, but I didn't change my mind. So we have to add a new degree of freedom, which is this degree of freedom over here. In our language, this is a left-handed, because remember, all the fields are left-handed. This is a left-handed antineutrino. Now again, people like to call that a right-handed neutrino as well, and you can do that because they are related to one another by complex conjugation. So that means if I have this new C field, I would like to have that allow the neutrino to get a Yukawa coupling. And the Yukawa coupling will be like this. How do we know it's H and not H twiddle? Because we know that the H twiddle combined with the L to give the charged leptons a mass. So we can't do the same thing back again because you end up with the same quantum numbers, and we don't want that. And of course, we can do the calculation. Remember, this is an isospin 1/2. And this says hypercharge minus 1/2. So I know how to combine these guys to give me an isospin singlet. I combine these two guys to give me a Lorentz singlet. The hypercharges already work out between the L and the H. So this is sufficient to tell me what are the quantum numbers of this new C field. So it doesn't have any color. It doesn't have any SU2, and it doesn't have any hypercharge. So again, this is SU3 cross SU2 left cross U1 hypercharge. So that's it. So that's a very simple way of giving the neutrinos a mass. Now the question is, if you've prodded around enough, you probably don't hear too much about these Dirac neutrino masses. So let me just conclude, by the way. Did my screen get bigger? Anyway, it doesn't matter. So the neutrino mass here is lambda nu V over square root of 2. And the square root of 2 is just from the definition of the VEV. So that's the neutrino mass. And the question is, why don't we like this model? And I want to talk about that probably more than I should, but there's a reason why people don't like this model. And that's this reason here. So this mu C is a gate singlet. So here we go. So that means we're coming back here. So if we were redoing everything that we were doing before, we would add a new particle here, mu C, to this table, and that comes with a 1, 1, 0. And remember, when I was talking about this, I told you that if you looked at all of these fermions and you started writing down all of the possible bilinears, you were not allowed to write down a fermion mass. Once you add this new C field, that statement is actually wrong. The new C is not just any fermion that you've added to the Lagrangian. It's a gauge singlet fermion. So if you have a gauge singlet fermion, this object here is Lorentz invariant. And it's also gauge invariant because, you know, the colors work out, the SU2 works out, the hypercharges work out. So this is something that looks like this. It's a Majorana mass for this guy. So that means I could write down in my Lagrangian a term that looks like this. Okay? And if you allow for this possibility here, then, as I'm going to talk about probably on Friday, if this M is not 0, then the neutrinos are not Dirac fermions. Okay, so before I continue talking about this, I do want to remind you of something very important, which is the symmetry structure. Of the standard model Lagrangian. And the standard model, of course, and again, there are lots of different ways of picturing what the standard model means, but a useful way is to say the standard model for me is a gauge symmetry plus fields plus Lagrangian. And the idea is the following. If I tell you the gauge symmetry and I tell you the fields, you can write down the Lagrangian. I have to tell you when to stop. So I say that the Lagrangian is renormalizable. Okay, so if I do this, then you get the standard model Lagrangian. Okay, if you follow this recipe, there's a fun fact, which is after you follow this recipe, there's some global symmetries. And actually, even once you include generations and you wave your arms a lot and so on, there are two symmetries. One is baryon number. The other one is lepton number. And of course, as everybody has heard many times, is these two symmetries happen to be anomalous. So they're going to be broken by quantum mechanical effects. But nonetheless, there's another symmetry that's left over, which is this U1B minus L symmetry. The key feature of this discussion is that if you look at this story here, at no place did I have to tell you that your Lagrangian had to have a U1B minus L symmetry. The U1B minus L symmetry comes out for free. We didn't ask for it, it's just there. And it's a side effect, if you want, of the gauge symmetry and the fermions that we have with the charges that they have and the fact that we're writing down a renormalizable Lagrangian. So we didn't ask for this U1B minus L global symmetry to the Lagrangian. It just happened. And again, you know, the language we use is, this is an accidental symmetry. Okay, so let me say a few words about accidental symmetries. What does it mean to be an accidental symmetry? It means we didn't ask for it. It kind of just happens. So that's one comment. What does that mean it means that if you write down a generic, extension to the standard model, you will break this accidental symmetry. And the reason is very simple. Since you didn't ask for it, and it happened by chance, then it turns out that if you start screwing around with the model, you will break the symmetry. So there's a comment here. For technical natural argument, we can make Majorana mass of nu c to be small, then it will not matter so much. I will talk a lot about that, but yes, this is correct. And I don't mind, so I will be talking about this Majorana masses for the right-handed neutrinos a lot. So hopefully that will address this question a little bit. Good. So again, so this is what we worry about. So these accidental symmetries of the standard model. And the final comment I want to make is just a weird comment, which is that this is a global symmetry. And if you have string theory friends, they don't like global symmetries. They will tell you that quantum gravity does not like or does not allow global symmetries. I don't know exactly what that means, but it's just something to keep in mind. And I think it's behind the psychology of us not worrying about Dirac neutrinos as much as I think we could. Okay, so this is accidental symmetries. So now let's go back to neutrinos. So we were saying here's a Lagrangian. And again, the most general Lagrangian I can write down is one that looks like this. And this is a great Lagrangian because it has a lot of the features of a generic BSM model. And the key feature of this Lagrangian is that it breaks U1B minus L. And the reason is clear. So this mass, you can't hide. You can say, okay, if I stare at this term here, if I say that the nu c has a 0 B minus L charge, and then if I stare at this term, the B minus L charge of the L is 1, and the B minus L charge of the Higgs is 0. Or if you want to be, this is B minus L, so it's minus 1. So if I have charge assignments that look like that, then you see that B minus L is broken. Okay, so I say, oh, so this doesn't work. So let's try a different assignment. And here would be a different assignment. I can assign, so let me erase this arrow over here. I can assign B minus L charge of +1 to the nu c. So if I do that, then this term here is fine, right? So this term is okay, but this term here is bad. So what happens is, if lambda nu is not 0 and m is not 0, then this U1B minus L is explicitly broken. That means it's not a symmetry of the Lagrangian at all. And we can't have that. Okay, so there's another question. Oh yeah, so there's a question about why not B and L, and that's because of anomaly. So thank you for answering that. Then the other question is, must we break the accidental symmetry in BSM? Or more like we can break it and we can still keep it? Yes, absolutely. So the statement I wanted to make is, if you write down a generic BSM model, you will break all of the accidental symmetries. If you don't write down a generic BSM model, you don't break these accidental symmetries. Again, there are lots of examples of that. Again, if you go back to supersymmetric extensions of the standard model, if you write down a generic supersymmetric extension of the standard model, it violates B minus L because of the what's called the R parity breaking terms in the superpotential. And if we don't write down those terms, then we maintain the B minus L symmetry. And that goes into the direction of what I want to say, which is the following. So, and maybe this will become a little bit more clear. So there's another question. Is the addition of Hermitian conjugate implied, or is it necessary? Yes, it's implied. Thank you. So I will make it less implied. It's always implied. And by the way, this one needs a Hermitian conjugate and this one needs a Hermitian conjugate. They're both things that come along with a Hermitian conjugate. Thank you. So where are we? So we have a Lagrangian where B minus L has been broken. There are ways around that. You know, I can restore B minus L by choosing, by not having this be true. So if the Okawa coupling is 0, then B minus L is preserved back again. But that's not a good model because in that model, the neutrino masses are 0. And you're just adding some new fermion to the Lagrangian that doesn't couple to anything. So it's kind of a stupid model. So we don't talk about that one. Then the other one is we can make this M equal 0. And if we do that, it's fine. Okay, if we do that, we choose M equals 0. So that means that this term is not here. And then the neutrinos end up being Dirac fermions. And that's sort of the avenue that we would like to go down. Now, if you choose M equals 0, so these, remember, these are the right-handed neutrino masses. It's from this term here. Then the neutrinos are Dirac fermions. And what I do want to emphasize is the fact that this is an interesting, reasonable choice that you can make. But the point is, if you go back to what I was saying here, which is, and this is very, very important. So let me do something about that. So remember, I told you, this is a standard model, right? These are the rules of how to construct a standard model Lagrangian. You know, if you talk to your neighbor and you tell your neighbor, this is my gauge symmetry, this is my fields, and I want you to write down the most generally normalizable Lagrangian, they will write down the standard model Lagrangian, as long as they know, you know, quantum field theory. But you don't need to add any extra information. Now, the point that I want to emphasize is that if I do exactly the same thing again, so if I say, here's my gauge symmetry, here's my particle field content, except that now I add a right-handed neutrino. So let me put the C's here. And then I say renormalizable Lagrangian. Now, if you go to your neighbor and you give your neighbor these rules now, slightly different set of rules, then you do not get the standard model plus Dirac neutrinos. And the reason is that your neighbor is very smart. Okay, so if your neighbor is very smart, in the process of taking these rules here and writing down the most generally normalizable Lagrangian, your neighbor will not be able to know that you want these right-handed neutrino masses or Majorana masses of the left-handed antineutrinos to be 0. That means you have to change your rules. And there's a question which I'll read in just a second. I have to add a new rule. So if I add this new rule, then now you get the standard model Lagrangian with Dirac neutrinos. Okay. So let me look at the questions here. So can we introduce additional scalar that breaks B minus L to use it in the order? Yes, you can. So I will mention that a little bit on Friday. And then the other question is the addition of the Higgs in this symbolic equation implied in the, yes, it is, absolutely. So I apologize for that. The Higgs exists. So let's put a Higgs here. And by the way, if your neighbor was worried about that, he's very smart, or she's very smart. And of course, you have to worry about all the whole electric symmetry breaking thing. But again, if she got this far, then she'll be fine. Okay, so that's the problem. So if you want to give the neutrinos a non-zero Dirac mass, and that's it. So if you want to get, if you think nature looks like this, then you've just done something amazing, which is you've changed the rules of the standard model. And you had to tell your friend that B minus L was a symmetry. So that means if you think that the neutrinos are Dirac fermions, then U1 B minus L. Or if you want to play around, it can be just U1 L that you then make non-anomalous in some way, is upgraded to a fundamental symmetry. Okay, and this is a very big deal because now all of a sudden, instead of having this U1 B minus L come out as an accidental symmetry, it actually has to be a fundamental symmetry. So if somehow you knew for a fact that the neutrinos were massive Dirac fermions, and again, I'll try to talk about that a little bit more, but if you knew for a fact the neutrinos were massive Dirac fermions, then you would have learned that U1 B minus L is a fundamental symmetry of nature. What does that mean? It would mean, for example, that every time you write down a BSM model, you have to be cognizant of the fact that U1 B minus L has to be there. So a whole bunch of BSM models are not allowed because they violate U1 B minus L. And then, of course, there's this weird business of what about your string theory friends that care about quantum gravity and the fact that quantum gravity doesn't like global symmetries. So if you knew that the neutrinos are absolutely fermions that are Dirac fermions, you would have to do something about that. Maybe the U1 B minus L symmetry is gauged, but it can't be gauged because there would be a new force. Or maybe the coupling is super small, and that's why we don't know about that. And all kinds of interesting consequences come out once you learn that there's a new symmetry in nature. Okay, so there's some questions. Any term with D less than 4 is also renormalizable. Yes, it is. Yeah, if you're talking about, no. If D means the mass dimension of the operator, that's correct. And I think that's the answer. So that's why, so this is allowed. This is a dimension 3 operator, and that's renormalizable. It's not a marginal operator, but it's renormalizable. So another question, are there any experimental tests about constraining the violation of U1 B minus L? Absolutely, and that's what I'll talk about. And there's going to be sets of lectures that will discuss this from the experimental side. And I will try to introduce this, I'm assuming not today because I'm running out of time. Second question, why don't we make the B minus L charge of the neutrino 0? The reason is very easy, because the neutrino is at the mercy of the charged leptons. Remember, the neutrinos live here, and whatever lepton number the electron has, the neutrino better have. I also mentioned that if you want to make the right-handed neutrino B minus L charge, you're allowed to do that, but then the Yukawa coupling explicitly breaks that. So you can't, if the Yukawa coupling and the Majorana mass are not 0, you can't escape that. And if you make the Yukawa coupling 0, the neutrinos don't get a mass. So that doesn't help. So finally, the last question, if the B minus L charge of NC is 0, okay, it's just a comment on what I just said. Okay. So I do want to finish talking about Dirac neutrinos for just a second. I do want to say that even after all of this, even though we learned something amazing, which is that B minus L is an exact symmetry of nature, we still get to explain the neutrino masses. You know, remember I said the neutrino mass is the Yukawa coupling times V divided by square root of 2. Now, there's a problem that people don't like. Okay, so one question. Why do we think make Yukawa coupling equals 0 not a good choice? It's a perfectly good choice, except that the neutrino masses are 0. The standard model neutrino masses are 0. And that's what we want to solve. So that means we don't get to solve the problem we set out to solve. So it's not a useful choice in that sense. It's a perfectly fine theory. But what you're doing is you're adding a new fermion to the Lagrangian that has no quantum numbers and no interactions. There's a comment. Can I understand that since neutrino carries B minus L and then the Yukawa coupling to the Higgs? Yes, that's correct. Okay, so the thing I want to say in the next few minutes is the other complaint that people have, which is, remember, I want the neutrino mass to be about 0.1 electron volts, which means that I need my Yukawa coupling to be about 10 to the minus 12. Okay, so that's how you fit the data of what the neutrino masses are. I want to remind you that the electron Yukawa coupling is about 10 to the minus 5. So some people will say that this is too small. I don't know what that means, because a 10 to the minus 5 is already pretty small. So I have no idea where the boundary is between pretty small and too small. But it is a generic complaint that people like to write down. And I think that a better way of being confused by this number and why is it so small, I think it goes back to this picture here. So the reason people don't like Dirac neutrinos is if the neutrinos are Dirac fermions, you don't really get a satisfying explanation for why are the neutrinos so different from the charged leptons. Again, this is not a scientific question. It's sort of an aesthetic question. But somehow, if the neutrinos are just Dirac fermions, then nature really missed out on an opportunity to do something exciting, because it managed to make these numbers kind of the same, even though they're different by 5 orders of magnitude. And to make this mass here so completely different, but to still have the dynamics that leads to these two kinds of masses be exactly the same. So that looks like, if nothing else, it's a missed opportunity for nature. Of course, nature really doesn't care about how we judge nature, but nonetheless, you know, we like to believe that this means something. Because I've almost run out of time, I do want to mention one model building thing that people get excited about that has to do with Dirac neutrinos. Okay, so again, I will write down this Dirac mass over here. And this is the coupling that gives the neutrinos a non-zero mass. And of course, remember I said that this number has to be super tiny, 10 to the minus 12. So how do we write down a model where this happens in some interesting way? And one way to do it is the following. So remember, I have this new C field. So imagine that this has a quantum number that we don't know about. It's a new quantum number. And it's a quantum number such that the L and the H are neutral. If I do that, then this Yukawa coupling is forbidden. It violates this new charge. So basically what you're doing is you're adding a new C field, but you're saying that it has some new charge that I didn't know about, and that new charge forbids the Yukawa coupling. And I'll answer the question in just a second, and I'll talk about an effective probably the next time. But if I do that, you know, if I give a new charge to this new C field, then I can't write down a Yukawa coupling, which of course is both good and bad. I mean, it's good because it explains why the neutrino mass is so small. It's bad because it makes the neutrino mass 0. On the other hand, if I add a new field phi, which also has new charge, then it could be that even though this is not allowed, I can write down something that looks like this. So imagine that, remember, just like in the standard model, the LH forms a gate singlet. Imagine that this new C phi also forms a gate singlet of some new interaction that we didn't know about. So in that case, so let me change colors here because this is messy. So if both the Higgs get a VEV and this phi field gets a VEV, then I end up with some Dirac mass for the neutrinos, and this mass is proportional to V, the VEV of this new field, and that's what it's proportional to. And the challenge of doing that, or the thing which is exciting or not exciting about doing this, is that this is a higher dimensional operator. So its coupling has dimensions of 1 over energy. So you get a neutrino mass that kind of looks like that. Okay, so that's the, let me put a little boundary. That's one idea that people have thought of that explains. So I'll write this over here because I'm running out of space. So if V over phi, V phi over lambda is very small, then you get tiny masses. So this is one kind of model. And since I've already gone over time a little bit, I'm not going to dwell on these very much. I just want to say that these models are exciting. They are very challenging to build because remember, this new C is a chiral fermion. And your model, if it's a new gate symmetry that you're coming up with, that means you have to add more fermions to cancel anomalies. If you don't care about anomalies and you want to make this a global symmetry, you're still explicitly breaking a global symmetry. That means you get Goldstone bosons, which is bad. You might also get domain walls and all other kinds of junk as well. So it's an interesting model building. And of course, the last thing I want to say is that this kind of thinking has a strong connection to dark matter because I'm introducing a new quantum number. So you can think about this as a dark sector. And of course, right-handed neutrinos are the poster child of dark sectors. They are some new state that came out of left field, and it's not charged under the standard model at all. And that's exactly what a dark sector is, and it kind of smells like dark matter stuff. Okay, I'm going to stop here for today, but I'm going to try to answer the questions. Let's see. Okay, good. So one question is, if the neutrinos were Dirac fermions, wouldn't the right-handed neutrinos screw up the N effective? The answer is they could. And the reason they don't is the following. If you go back to the plasma in the early universe, you have to ask yourself if the right-handed neutrinos were ever in thermal equilibrium. What's nice about the early universe is that we don't have to care about masses at all. So we can just treat the left-handed neutrinos as 1 degree of freedom, the right-handed neutrinos another degree of freedom. And the question is, can these right-handed neutrinos ever be in thermal equilibrium? The reason is for them, being in thermal equilibrium is very hard because the only interaction they have is the Yukawa interaction, this one. So they only have this interaction. And on top of that, so let me point at it in some better place. Here. So this Yukawa interaction. And I just told you that this coupling here is 10 and minus 12. So you can ask yourself, can the right-handed neutrinos ever be in thermal equilibrium? The answer is absolutely not. So very, very generically, you can say that even if the right-handed neutrinos were produced after inflation, as the universe was cooling down, they're going to be super cold. So just like the neutrinos are a little bit colder than the photons, the right-handed neutrinos are really cold relative to everybody else. So their contribution to an effective is 0. So they cannot be constrained that way unless they have more and more interactions. So hopefully that's kind of clear. So another question, are there any specific choice of breaking scale phi can be, okay, so that's a good question. So in talking about these models, there's a bunch of models like this, by the way, where you introduce a new scale. You do have to address this, which is not particularly hard to do, but it basically gives you a multi-scale model, because you have to have a scale associated to the breaking of phi, and then you have another scale which has something to do with this higher dimensional operator. But you can work on this. This happens, for example, in what's called the mirror world models. So if you ever heard about that, you can see things that start to smell like this kind of higher dimensional operator. Okay, other question. Why not have something like H nu C phi? Yes, except that H nu C phi is a fermion. There you go. Okay, so there's a comment below that. It doesn't work. It doesn't work even because it's a fermion. Remember, phi here is a scalar. So the reason for why nu C carries B minus L can allow us to write down its mass because blah, blah. I think that's, so again, going back to this, if I want the Yukawa coupling to be there, and I want B minus L to be a good symmetry, then the nu C must have B minus L, which means that the Majorana mass is not allowed because it violates B minus L. If that's what you meant, then that's correct. There's nothing to do with hypercharge. And finally, can you repeat why the standard model fields have to be neutral under the new charge? They don't have to be. They can also be charged under this new charge. And that's just a very different model. This again also goes back to dark sector models that Martin talked about last week. Once you start giving standard model fermions new gauge quantum numbers, life gets hard. You have to worry about a lot of phenomenology, but you can do it. I mean, there are all kinds of ways that you can invent new charges and new symmetries and new particles charged under that. But because our job was to explain why there's no renormalizable neutrino Yukawa coupling, and the hope is that we still want to make sure that all of the other Yukawa couplings are renormalizable, then the easiest way to do that is to charge the nu C, but to make sure that the LH is not charged. So that's the point. Okay, so one more question. So why not just keep Majorana mass and you see some, that's what I'll talk about next time. So again, what most people do, including impatient people, is to say, okay, this U1 B minus L thing is clearly very messy. Why don't we just live with both of these couplings at the same time? And that's what I'll talk about the next time. So yeah, so the most general thing you can do is to have all of these terms there. And the reason I want to get rid of one of them is because I want to make sure that the neutrinos are Dirac fermions. If they're not, then there's no reason to go through this song and dance of explaining why this is 0. So I will talk about that next time. And I'm pretty sure I'm out of time. Oh, yes, I'm pretty sure I'm out of time. But if people have more questions, if I'm not out of time, the organizers can let me know that I don't know how to read the clock.
You're not out of time. You know, at some point we should decide that all this stuff gets shifted over to the coffee break. But I see one more question there. You can certainly answer that one.
I'll take that one.
Then we can go get lunch.
So we're using spontaneous symmetry breaking of Z2 directly lead to the main wall. I don't want to talk about the main walls, but that's generically what happens. If you break some discrete symmetry, you get these topological objects, and then they tend to overclose the universe. Again, you can model, build your way out. You can use the dynamics to get out by having things happen before inflation. So there are all kinds of choices. But in the case of of what I was talking about, the biggest concern is if you spontaneously break a symmetry that's not gauged, then you get a Goldstone boson, which is a massless scalar in your theory. And then you have to go back and ask yourself, is the massless scalar in the theory allowed and not completely ruled out by experiment? And I think that's the biggest concern there. The domain wall is just an extra concern that you have to worry about. So my answer is I'm kind of punting on the question.
Okay, so Andre, where are you going to take your coffee today?
Oh, yes, good. So I will be in room E again.
Okay.
If people have more questions, I'm happy.
Do you have anything, any notice from any of the other lecturers that they might show up and hang out? Or is it going to be just pick a room and wander around?
Yeah, so I think as we've been doing, we'll just let the lecturers follow their nose.
Okay.
And see what happens. Yeah, I guess we forgot to ask if Eric wanted to be around for the coffee break today, but he might be. So if two of us are in the same room, we can try to coordinate.
One of you leaves.
Yeah,
okay.
But I'll be in room E.
Okay. Okay, so I guess we're done. So coffee is at 1:30, and the next talk, that's Lisa at